Yeah, today I will be talking about investigation on wave propagation through atmospheric turbulence for adaptive optics. So, what is the motivation of this speech talk is that wave propagation analysis through pseudo-random phase space normally gives input of what we are trying to do here is that we simulate atmospheric turbulence using a pseudo-random phase plate which rotates with respect to a particular speed. So when the light propagates through that, it can create an atmospheric turbulence similar to the in space what we are witnessing. For example, when you go, this is actually the real scenario. So we have a distant space object above Earth about 2 kilometer, 3 kilometer. We have because of S radiation, there will be a turbulence. So turbulence between 1 kilometer to 3 kilometers. So this actually degrades distant objects. So it will be a problem for astronomers from Earth-based telescopes to witness distant objects. So there are, though it is not temperature fluctuation is very minimal compared to the other temperatures, but this can introduce severe, beam wandering, beam degrading. This will degrade the quality of the image. Actually, we have conventional lens systems where we have a lot of aberrations like coma, astigmatism, spherical aberration, etc. But these things will not affect this turbulence. But turbulence affects in long term, particularly very long distance images like galaxies and stars. Particularly twinkling of stars is actually attributed to turbulent effects. Now there are several, though it is a very narrow topic which very few people work in the world. But in IIST, we thought of developing some technology, adaptive optic technology, because ISRO also interested in developing some adaptive optic technology to correct these aberrations. Because ISRO has 1 or 2 telescopes in Mount Abu and some I don't remember exactly. Mount Abu one telescope they have. They also have Lay. So we are trying to use this technology, whether it is possible for us to develop conventional adaptive optic techniques to solve these turbulent effects. So this is actually the figure shows that light coming from space object, for example, star passing through turbulence, which is the fluctuations between 1 to 3 kilometers of Earth atmosphere, and falls on a telescope, and image is like that. You can see that you can have a horizontal layout also and vertical layout also. So the main aberrations are beam wandering and scintillation, which are intensity spread actually technically. What are the characteristics of turbulent flow is that the turbulent flow can be chaotic, it can be disorganized, seemingly random behavior, it is not repeatable. Depending upon the conditions, summer it will be there, 2 o'clock one condition, 2 or 3 o'clock one turbulence, like that it can change. It is not temporarily stable, definitely not temporarily spatially not stable. So extremely large range of length and time scales you can have. And enhanced diffusion, mixing and dissipation of both are possible in this scale. And it is actually 3-dimensionality, time depends rotationality. Hence potential flow cannot be turbulent because it is by definition irrotational. So intermittency in both space and time. So these are some characteristics of turbulent flow. Basically, this can be analyzed using fluid dynamics. Actually, Professor Kalmogrov of Russia earlier, he developed this. Actually, he developed for fluid flow, but it can be used for turbulence effect also. What are the atmospheric turbulence? Different temperatures lead to this one. You can see that the solar radiation, wind shear, convection. This you can see that how this can be considered. You have an outer scale. You also have inner scale, and this looks like a small inner scales with small this one. These are some temperature fluctuation. You can see that outer scale radius and inner scale radius of this one, which actually creates this L0 is small eddies we call, and temperature fluctuation. Similarly, outer scale also we can see that, but it's very difficult to model it, and this is what we have. But you can correct this atmospheric turbulence using adaptive optics. So what are the techniques we have? Both we have conventional and unconventional techniques to study the, like we can actually shoot with a very high power laser in space and find out, we can create an artificial laser, the artificial star like beacon, laser beacon, from that, what we can actually characterize the atmospheric turbulence atmosphere, and accordingly we can correct it using a control systems. So we can also have this character. The character has actually deformable mirrors. What deformable mirrors means, when the light passes through that, accordingly the mirrors will deform. This can be made using MEMS nowadays. So when there is a beacon sends a signal back, so accordingly this signal goes back to the character. Character is made up of deformable mirror. So that will adjust the character, aberration, and it gets to control computer and feedback back to the wavefront sensor. So this is what a loop. It's a small loop where one can use correct this atmosphere. Not very easy. It looks very easy, but it is not that easy because there are other constraints involved in this understanding of this. Now, normally we can use wavefront sensors. There are several technology now involved in wavefront sensors. People are developing different type of wavefront sensors. One of the popular is Shack-Hartman wavefront sensor, which I will be telling you a little later. Then you can also use shearing interferometer. We can also diaphragmatic reflective mirror and curvature sensors, and also we can use our conventional phase conjugation method. So phase conjugation, as you are aware, when the light passes through the aberration, it can invert the phase. That's why that in phase, you can, when it comes back again, it passes through the aberrator. It can correct itself. So there is a possibility of using phase conjugation, but unfortunately, creating a very large level phase conjugation, it will be very tough nowadays. So that is a problem there. So deformable mirror is the best solution so far the adaptive optics systems are concerned. So you can see that this is our character, which is made up of deformable mirrors. Light coming from laser beacon. Laser beacon is nothing but when you shoot a laser into the star, into the space, due to the upper atmosphere, there are molecules and it can scatter and create an artificial star. So that is what laser beacon means. So that can give you, when it passes through when the light of laser beacon passes through the same turbulence, it will behave like that. It can pick up the turbulence impact, and that which can give back to the via telescope. It can give back to the character. Then we can correct it. So character is normally a deformable mirror, or it can be a this one. Sensor is a wavefront sensor. This is what actually happens in the system. Now, what are the literature? Normally, the main literature which adaptive optics people imaging through turbulence people feel, that is Kolmogorov. There is one very nice article. It is in Soviet physics .lad. I don't know whether it is available. The local structure of turbulence in incompressible fluids, very large Reynolds number, etc. Tatarsky is PhD student. His thesis is very well written. So that is, he is written about this wave propagation in turbulent medium. His student Tatarsky, the student of Professor Kolmogorov, and it is available as a book. And we can also have other this one. These are the main two books which normally adaptive optics follow. Now, what is meant by, there are two important functions involved in atmospheric turbulence. There is known as that are known as structural function and correlation function. The structural function is mean square difference. I just give a brief introduction to the mathematical experts. So d phi is a structure function, which is phi at a position at 0.1 and phi x plus another position. So modulus of the square ensemble will give you the d phi value of that, which is called phase structure function. It's called phase structure function of light being passing through the turbulence, and this can be measured like that. Similarly, covariance function also we can introduce. The spatial random variable is given by v phi. Is again x plus r phi. It is related to the phase of the light being passing through the turbulence. So these are two important functions in phase functions. Now, what is the basic relation between structure function and covariance function, which can be given by d phi r by 2 phi by 0 phi r. This relationship can be expanded to assume homogeneity. We assume that this is at particular time the turbulence is as homogeneous. It can be inhomogeneous at a different time. Now, what are the you can evaluate the spatial coherence function, which is very important for understanding the light propagation through turbulence. So the exponent I psi, which is actually a random variable psi, can be written as exponent minus x square by 2, and c psi is in a spatial coherence function, which can be used for finding out the structure function d phi in this form. So we can use this spatial coherence function in this form, in this equation, which is possible for us to measure the important d phi value of this function, structure function. Now, what are the definitions for spatial coherent function? For a light wave which has a amplitude and phase is per e power I phi, the phase is given by kz minus omega t. If the light propagates along z direction, and omega is the frequency, and we have the spatial coherent function can be defined as c psi equal to psi type. So this is the spatial coherent function. This c psi actually measures how the phase is related to the field at one position x to another point x plus r. So in space, at one position, what is the phase of the light, a light wave, and how does it behave in another position? So this is not, the psi is not a complex field with this space. This we should not confuse with. Next one is how to find out, evaluate c psi. We can evaluate by using e to the minus d phi r by 2. People have measured these values for various atmospheric turbulence, various places in the world. And it is available in literature with these values which we can find out using from B phi is available, D phi, all these are available for various turbulence functions, and these are some parameters which we can use it. And in phi is actually you can give h into delta z with using we can measure, where n is the refractive index for a wave propagating vertically in z direction, and h plus delta is height, n is the refractive index for fluctuation, refraction of the medium. And here it is a turbulent medium. So V phi can be measured. If you know the refractive index values, you can measure in this form at two different positions. And what are the other terms of the turbulence which we can use? We can also use the change of variables and try to find out V phi in terms of refractive index at one point x plus r and z plus position. Similarly, the V phi can be also found out in vertical direction, and we can use these variables for finding out. Now these are all available as literature at various heights, and what are the normal. You cannot measure every time because this can change. So it is not a constant value. So we have to measure at this particular question, Trivandrum, what is the height, how much turbulence it is there. In Karakoram it will be different. In Valiamala different like that. It is different values. So depending upon this temperature, particularly refractive index fluctuations are very random. Including in a particular city, it is very difficult to pinpoint if this is the exact value of refractive index fluctuation. So then we can evaluate d phi if you know all this b phi and all these parameters. The particular distance, height, it is possible for us to measure. And here also we can measure various positions with these values. D phi is a very important function for finding out. And actually the turbulence strength, Cn square, is also we can find out. And this is also given in literature, various values of Cn square at various times, whether summer, winter, and autumn, and various seasons. This can change, and these values can be used. What are the terms which we can? This also can be Dn can be written as in this form, and Cn square is equal to all this form, and we can finally find out approximately the values are given here by substituting the known values. 2.91514 k square r phi 3, which is Cn square delta S value, which is given by, and these values you can find out from literature, and one can get it from this. But I think it is not possible for us to use, better to find out then and there, so it is not easy to find out these values. This will not suit for Trivandrum if they do it in somewhere in Bombay or Delhi. So these are the problems in this one. We can evaluate the spatial coherent function using these values. And for a slant path, for a horizontal path, you can have secant square eta by 3 to count for depends on zenith angle eta. So this is actually the summary of how to find out the spatial coherent function using d phi phase structure function, and from the refractive index fluctuation and the phase of the light beam passing through the atmospheric turbulence. And these can be measured. Now, what are the spatial coherent, the effect of telescope? How it is affecting the telescope resolution. So the optical transfer function is normalized autocorrelation function of amplitude transfer function. Okay, and also R0 is the telescope diameter, where the two optical transfer functions are equal. The expansion of R0 in terms of phase structure function for a telescope is given by in this formula. So 0.423 k square secant square eta from 0 to height Cn square as this value. If you put, it is possible, it is proportional to the wavelength of the light passing through the turbulence, and we can calculate these values. So this actually again it is also measurable for a various telescope diameter, and it is we can use it for people have used these values of this one. What is the scaling of R0? R0 is the sub-aperture of the telescope. In adaptive optics correction, this is approximately given in this form. So R0 gets smaller when turbulence becomes stronger. Why R0 is very important? Because the turbulence is very strong, and for a large value of the space structure function Cn square, R0 can get smaller, and it can be bigger for very longer wavelengths also. So longer wavelengths only it gets bigger, and adaptive optics is easier in the infrared than with this. This is a very important factor is that instead of using visible light, it's better to use infrared. I think as you are aware that even fiber optics communication, we can use free space optical communication. It's a very convenient range because infrared is a convenient range. So adaptive optics also very comfortable with infrared because it's the R0 value can be bigger. Once R0 value is bigger, it's easy for you to image through the telescopic imaging. So R0 gets quickly as telescope looks toward the horizon. So it's also very for horizontal it will not be very successful because it can the zenith angles are very low. So it is not possible. I think it's better to use adaptive optics with infrared as a prop light passing through atmospheric turbulence, and we can, when you use this telescopic system, it is possible you can measure this catching. Now we have in lab, we can create atmospheric turbulence using a small setup which I will like. This is the setup which we use in the lab, where the turbulence simulator is shown here. It can rotate with respect to different speed, and I will explain to you the turbulence how we simulate it later using the explanation of this the plate which rotates inside the medium. So very simple one. So this is called the pseudo random phase plate, which we have. We can also make it which rotates with different speed. This is a pseudo random phase plate which can mimic atmospheric turbulence inside the lab. So this consists of, this is the details of this pseudo random phase plate, where you can see the phase structure. This is actually designed for infrared propagation through atmospheric turbulence, and it is having a 4096 square grid, which all these diameter parameters. So you have a 5 phase this one. We have 2 BK class ordinary glass, which is sandwiched inside an acrylic, and near infrared near index matching polymer can be coated here, and it will exactly measure the turbulent fluctuation. You can measure the atmospheric, whatever typical atmospheric turbulent refractive index you can simulate here. You can actually get it when the light passes through this pseudo random phase plate. So it is actually designed for measuring the turbulent impact using wavefront sensing, which this can be used for adaptive optics system. It is exactly mimicking atmospheric turbulence similar to any in real-time sense. So this is one of the very important phase plate. Actually, it is developed in DRDO way long back, and now an American company has taken the patent of that, and they are manufacturing this. This also can be done in our India. Also, is not very difficult to make it. In other ways, you can also heat the water and create the steam. Also, can give you atmospheric turbulence. So here it is a very important thing. Actually, we got it from DRDO, IRD Dehradun, where they are designed and given to an American company. So through that only we got it, and it is very nicely, and stepper motor and all we can always. So you can see that this there is a stepper motor here which can rotate with a different speed. And only thing is our detecting system camera should be the same speed we have to align, so that it is possible for you to measure the exact atmospheric turbulence in the lab. And this pseudo random phase plate consists of 5 layers: the 2 outer layers of BK7 and 2 inner layers of near index matching polymer, and 1 layer of acrylic with a turbulent profile. So we can always encrypt a turbulent profile onto it on one side. And this is 3:28 inch acrylic annulus with 1.35 diameter obstruction in the middle. The 2 PRP actually we can with the 2 PRPs are different in the sense of free coherence length. The PRP in our laboratory mimics atmospheric turbulent at the wavelength of infrared 1550 nanometer, as reported in the manual which we have purchased. And this is actually mounted on 2 separate computer-controlled stepper motors with a single driver, so this can be operated at different velocities for creating time-varying phase fluctuation of atmospheric turbulence. So this is the exact explanation of pseudo-random phase plate. Now, how do you calculate this one? So we have we can make single passage, phase matrix, double passage, all this thing we can make it. And we can find out d phi double using these manners. The corresponding phase structures function also can be calculated by phase single and double matrices. We can find out the ensemble averages also using this. This phase structure function can be found out in this formula. I don't want to go in detail about these mathematical formulas. So this we can measure using find out from the radius. And you can also use determine the lower power for the Kolmogorov case, and we can find out the consistency parameter from all these values. Coherent results we can calculate using this turbulence, and we can also find out various values for values of Kolmogorov for slope V2 and etc. Now, one of the important approach of finding out the turbulence effect is that there are several years back, Professor Simon and Mukunda written a paper on wave propagation through how electrolyte beam propagation through in free space. One can use this variance matrix. The variance matrix actually gives you the similarity. It's not actually quantum mechanics, but it can give you a similar approach to. It's a classical. Since our measurements are in classical, and we can use this variance matrix, which actually obeys somehow things are obeys uncertainty principle, and we can use this variance matrix for finding out the phase fluctuation. Actually, it is parallel, conventional operation like coma, piston, all these things. You can also parallelly we can find out using variance matrix the corresponding values of light propagation through atmospheric turbulence are in free space. So actually, this is one of the very famous papers written by Professor Mukunda and Simon. And this we have used to find out whether it is possible for us to use the find out the characteristics of atmospheric turbulence using variance matrix. So we assume that a monochromatic scalar wave field or beam propagating along z direction can be expressed using this form. Psi is the amplitude, and e power minus 2 pi nu t is the phase of the light beam passing through the turbulence. And this is transverse stability like one. The transverse phase dependent apart from z can be given in this form, where AXY denotes the amplitude. Now we can find out using variance. There are various variance matrix. There are different constituents of this variance matrix. One of this one coherent wave field is using 4x4 we can variance matrix. We can use this concept of variance matrix Vij for as given in this form, delta psi Aj for Jij various values of 1, 2, 3, 4. Here x denotes the position, x minus ensemble architecture. Px represents the slope of the wavefront. Px actually is the in terms of quantum mechanics it is actually momentum. Here it is actually along one direction. X is the position, and here Px is given you the slope of the wavefront. We assume because we cannot measure the momentum, so we actually give you we can measure the slope of the wavefront when the light propagates through the atmospheric turbulence. If you measure the position of this light beam along x transverse direction, you can have x and y point. Now, when you introduce turbulence, the points shift to a different position. So, when you take the slope of this wavefront, this will become px along x direction and py along y direction. So, we can use this concept of slope equivalent to momentum of the light in quantum mechanics. We can use this concept. Is definitely it is not a quantum, but it is actually parallel to that. This is what proposed by Professor Simon and Mukunda way back to analyze the different shell model beams, different topological beams when they analyze they propose a theory, variance matrix theory. So why don't we use it? So we try to use and measure the turbulence in a different form. So this is actually the variance matrix. So you can see the axis x square, the cross term xpx, xy, xpy. This is the 4x4 matrix which we have, and these can be measured like this. C1 is equal to modulus x, modulus y, and px, py. And if you measure all these points using a sensor, it is possible for you to get back all the members of the variance matrix one by one. So what are the variance matrix which we have in this case? And these are the points which we have. This is cross correlation point. So x square, px square, y square, p is a diagonal element and cross diagonal element. It is possible for us to. These are actually proposed by in the paper. So we try to measure whether it is possible for you to measure using variance matrix components using the turbulence in the turbulence. So these are the variance matrices. It can be written as V11, V12, V21, V22, where V11 is given by this form. So we can separate into 4 by 4, and each term, crossed V11 gives you, you can see that delta x square, half delta x dv. Similarly, here also the V12, V21, etc. Is transpose of the matrix, which can give you in this form. So V22 we can measure. So these are the constituent, and remember, is the number of this matrix elements. These are the matrix elements which you have, and this can be measured actually in the system. Now, what is the how to measure that? So we can use Shack-Hartman wavefront sensor, and this actually is our experiment has about 150 micromans lens array. Actually, Shack-Hartman wavefront sensor consists of n number of lens in the upper side and n number of downside, like a matrix. So we have around 150 micrometer focal length lens array with 12.8 to 1024 pixels of CCD in its focal plane. So we have a lenslet array. In its focal plane, we have a CCD detector, and with each pixel size is given by 4.65 micrometer into 4 into 65 micrometer. We select 1224, 1024 pixel size in the series of our analysis of this variance matrix elements. So each variance matrix element we can find out from this. And a Shack-Hartman wavefront sensor, technically, Shack-Hartman wavefront sensor, if you it can be divided into, this sensor has a CCD area, detection area, can be divided into 31 domains. With these domains, we can label I and J starting from topmost left corner to this, and we can have the positions of this wavefront light impact on this. So we can divide into these domains, and then we can measure it. Similarly, the Shack-Hartman wavefront sensor, when the light is a parallel plane beam, then it will give you exact spot in the center of the focal length of the each lens will give you a bright spot, red spot. Actually, red spot gives you exactly, there is light is a parallel exactly collimated. So the idea here is that in the lab we can exactly collimate the light, and we can make before passing through pseudo random phase plate, you will get the points here. Once the light is separated, you can see the shift in the position of the focal points. So this point will give you here, so that will give you a slope. So if this is x along x direction, you will get px along x direction in the after passing through the turbulence. Similarly, if it is y, after passing through turbulence, this will give you py. So we can measure exactly x and px value, y and py value along x and y directions before turbulence, before light passing through the turbulence, after light passing through here it is pseudo random phase state. So it is easy. I think there is a coherence between the variance matrix approach to Shack-Hartman wavefront sensor. There are very interesting paper based on that. But this is the first time what we are trying to do. Actually measuring in our lab, we are the first in the world in actually to measure using variance matrix the aberration. Now our aim is to whether it is possible for us to correct this using same technique or some other technique without adaptive optics, which we are trying to our aim. Anyway, the spot centroid and intensity coordinates corresponding to each of these domains are labeled xij, yj, and respectively. The spot centroid data for an ideal plane beam is equal to x0, and this is called reference points. And when there is a shift, you can find out the center of grid is coordinate will pixel is converted to okay. Now, when there is a shift, we can go to px and py. That is the idea of this particular measurements. Now, the deviations of captured spot centroids with respect to the ideal plane wavefront spot centroids is given in this form. So the phase of the light beam is actually that. So the phase of the light beam can be measured xij minus xuj divided by f effective of the lenslet array. Similarly, it is given by lambda into dou phi by dou x. Similarly, yij in y direction, dou phi by dou phi, where effect is the effective focal length of the lenslet array. Using the spot deviations and intensities obtained from the Shack-Hartman wavefront sensor, each element of the variance matrix of incoming wavefronts can be measured at a particular z coordinate distance in the system. So, if I want to measure the turbulence impact at a particular distance after the turbulence, z1, z2, different distance, which can be mapped into height. For example, from Earth 1 kilometer, 2 kilometer, when you do in the laboratory, same thing can be mapped into the space, and we can measure exactly what is the turbulence effect on the beam. So the model, this example of X, which we can measure from the Shack-Hartman wavefront sensor, we can calculate the elements model which I showed you in variance matrix in this form. If you know intensity when you can measure, position we can measure. So Xij, Yj will give you models of X. Similarly, Y direction you can get this value. If there is this X and Y gives you exact position of the intensity of light when there is no turbulence. Now, when you set the pseudo random place rotating with respect to particular speed, with respect to CCD speed, then the slope of the beam Px can be measured. The original position, displaced position X, then original position divided by F into intensity will give you the new position, which is nothing but your modulus of Px. Similarly, this also will give you Py along Py direction, Y minus Y0, the intensity of light we can measure from the data of Shack-Hartman wavefront sensor. We can measure each element of X, Y, Px, Py, which is responsible for the variance, which comprises each element in the variance matrix. So modulus of X square also we can measure, which is given by in this formula X square I dx by dy. Actually, this also can be programmed in MATLAB. There is no difficulty in doing this. Many postgraduate students in physics can do it, or graduate students can easily do this. There's no difficulty in doing that. Similarly, half X Px also we can measure. We already know X value, Px value. From that we can find out. This is nothing but slope of the wavefront. This is given by X minus X0. I is the intensity. We can measure these values. So next one is similarly Y direction we can measure. Model Y square, we can measure all these points from the data obtained from Shack-Hartman sensor, and half Y Py, the cross product also we can measure along Y directions. So another similarly Px square we can measure. Px square is lambda cut means lambda by 2 pi whole square, and we can measure 1 by 4i and dou I by dou x square. And from these values we can see very clearly how to dou phi by dou x. From the intensity value we can easily measure. This all can be calculated from MATLAB programming without any trouble. So each point, each Px, Py you can measure along X direction and Y direction before light propagates through turbulence. After propagating, this is for particular distance, and you can change the distance, measure again these values, and change the refract to this one. Similarly, Px, Py also we can calculate, and this is a cross product, so we can find out these values using intensity measurements from Shack-Hartman wavefront sensors, and these are some values which we have we can obtain based on these points. And what is the uncertainty principle in variance matrix? Actually, by definition, variance matrix will obey uncertainty principle as per the example. So V plus I lambda by 2 is greater than 0, so we can measure beta is in this value. So it actually obeys, variance matrix will obey the uncertainty principle. It is a parallel to quantum measurements. What is the symplectic eigenvalues? We can also measure symplectic eigenvalues of V beta square in terms of actual eigenvalue is the spread of light beam, kappa 1 square, kappa 2 square, kappa 1 square. Actually, symplectic eigenvalue is giving you the spread of the light beam in this K1 kappa 1 actually known as symplectic eigenvalue, but of variance matrix. But this actually characterizes the spread of the light field. And the uncertainty principle actually obeys kappa 1, kappa 2 obeys lambda by 2. For a coherent Gaussian wave field, we can have kappa 1, kappa 2 equal to half in lambda by 2 pi units. Thus, for coherent wave field, any departure of its K1, K2 from saturating value, so you can see that when there is a change in this value, you can see that there is a presence of higher order modes in the wave beam. So we can measure the modes of the light beam also. If you know the value, because the spread of the light field will give you from this variance matrix, you can calculate kappa 1, kappa 2, which I will show you a little later, and how to get back all these points. Now, another important parameter, twist parameter, is also optical angular momentum of light beam. Normally, it is related to twist of the light beam, which is normally given by this form. We can measure from the variance matrix element the twist parameter of light beam, 1 by lambda by 2 pi by lambda into x py minus y px. This also can be measured, and this is a measure how much a wave field twist as it propagates along the xz axis. So we can measure the twist of the light beam, and when it propagates along the z direction, if you know the variance matrix element with respect to the turbulence effect. So the turbulence, whether really it gives you the wave field twisting it gives you or not, we can measure it. In fact, when the light propagates through atmospheric turbulence, when the light and this can also behave like a different type of twisted beams, which we are exploring it. Depending upon the strength of the turbulence, one can understand the twist of the light beam. This also can be used for cryptographic applications, where if you know the twist of the light beam through turbulence, we can definitely use it for one of the key parameters, classical cryptographic, you can use it for, which is very difficult to break the secret key if you use this twist parameter of light beam passing through turbulence. So turbulence can be one of the very fine, cryptographic key, which we have used in one of the experiments, which came into very correctly. So this can be used for cryptographic applications also, if you know the twist parameter of light beam using variance matrix analysis. We need a very simple experimental arrangement to find out. Another important thing is, the variance matrix also can give you, this symmetry and asymmetry of the light beam. But the light beam is actually symmetrical or asymmetry using V delta. The trace of V1 minus V2, matrix 1 can be found out. From that, we can calculate the symmetry and asymmetry parameter of light beam. This can be compared to two wave fields at this level of the second order moments. Second order means modulus dx square, and the light can be found out. So the quantity can be used for wave fields at the level of second order moments. And here, this is called symmetry and asymmetry. The two wave fields are identical. Then you can say that these are all VQ equal to 0. And if they are not identical, then it will take a value between 0 and 1. This is one of the important calculations of this one. So the symmetry V delta can also be used to capture the asymmetry of a wave field in both x and y directions. Assuming V1 equal to V11 and V2 equal to V22, in the equation which we have shown here, we can find out if the wave field is symmetric. If that is V asymmetry should be 0 for a perfect wave field in the symmetric side. Similarly, if there is asymmetry, then you can see that there will be a value between 0 and 1. So we will normally use both V delta and V asymmetry in our experiment to calculate how much this turbulence impact the wave propagation through atmospheric turbulence. So it's very difficult to point out this one, and we can. So the experiment is very simple. So we used a simple helium neon laser, though the maid is made of infrared. This one we use a simple helium neon laser, and then we put a Shack-Hartman wavefront sensor at a particular point, and we can reduce this intensity by using various this intensity we can reduce by neutral density, or you can have a small power laser, because the intensity of the Shack-Hartman sensor cannot get more than 1 milliwatt or 2 milliwatt power. So we have to reduce the intensity, and we can measure at the various intervals. So what we have done is about every 2.5 centimeter. We have measured from the laser this more than 300 samples of turbulence we have measured, and this is what we have done. And we have similarly, after that we introduced the pseudo random phase split with different speed. So from this, what we can say that the height, we can assume that this is various distances. We can measure the variance matrix values, and after introducing the PRP, we use 24 centimeter from here, and is based at distance, and we measured the total variance matrices of the wave field. By rotating this PRP at various speeds, we can measure the variance matrix elements, and to generate the wave field sample, the PRPC is rotated at a speed of 0.014 rotation per second. The recordings are made with the Shack-Hartman wavefront sensor. Exposure time is about 0.079 millisecond with a minimum rate of 15 Hz. The time interval between the successive samples is about 66.779 microseconds, milliseconds. Sorry, for all practical process purposes, the PRP is deemed to. So this is very important point. For all practical purposes, the pseudo-random phase field should deem to be stationary with regard to the detector of Shack-Hartman wavefront sensor measuring the time scale. So actually, it is stationary. We are measuring at the stationary value. We are PRP. We are trying to fix it up like that. So now all of them are found to obey the uncertainty principle. Consider the variance matrix which obey the uncertainty. So we have, first we measured this parameter. You can see that the black line gives you the twist parameter without turbulence, and you can see the fluctuation, the twist of the light beam even without, for a simple Gaussian beam, you can see the fluctuation not very high, but actually you can see that some fluctuation are still there below 0.5. Now once you introduce atmospheric turbulence, you can see the fluctuations very high. Okay, it is not, in fact, light beam with respect to the fluctuation of these parameters are very important. And this for turbulence, what we have measured using helium neon laser, though remember that the PP is designed for that infrared wavelength 1500 nanometer, but still we are able to get the fluctuation of light in the turbulence in this way. That is, this is for black measures without turbulence, and the red measures with turbulence. So it's a very important point which we have given. Similarly, we have symplectic eigenvalues. So symplectic, the beam spread of the light beam. You can see at how many samples we have measured. The kappa 1, kappa 2. So this is this is without turbulence, black line, and the red line is with turbulence. You can see the shift in the position of kappa 1, kappa 2 are not different. The two different directions. You can see the beam spread along, one is between 0.5 and 1. The second one is between 1 and 1.5 or 1 and 2. You can see that the various samples, the same sample, sample number, same distance we have calculated at exactly 64 centimeter. We are able to measure exactly the height of this one. You can see that there is a change in kappa 1, kappa 2, and this is beam spread in the light. And you can see that the fluctuations of kappa 1, kappa 2 at various distances, 34 centimeter from the turbulence, 39, 44, various distances. You can see approximately with the black also gives you some fluctuations. At 54 centimeter, you can see that without turbulence also it gives you some height, and with turbulence definitely it gives a little higher. And you can see the difference for kappa 1. Similarly, kappa 1 here for fluctuation in various distances. We can have mean value of this one and actual fluctuations. Similarly, here also mean value of that, actual fluctuation. These are all can be measured using MATLAB programming. We students are capable of doing it. And these functions gives you a large number of fluctuation in light beams, which are useful for measuring these values. Now, what are the distance measures, symmetry and asymmetric values? One of the very interesting observation what we have seen is that you can see that asymmetry value black is very small here for various samples, and various distances you can see the fluctuation increases for asymmetry is increasing for this one. And whereas in the case of this distance, and the distance, this is for a particular distance. The first graph is for the A graph, the first graph is for particular distance. You can see the fluctuations going high at a particular distance. When you change the distance, 34, 39, 44, you can see that very interesting result that for a black is for without turbulence, whereas red is with turbulence. So it shows the symmetry is reducing at the various distances for turbulent impacted beam. For a turbulent impacted beam, you can see that red is a turbulent impacted beam. The fluctuation is very low, almost zero after 49, 44, except some fluctuation here. So this is a very interesting study that without turbulence, you can see the fluctuation more. For symmetry is, asymmetry is more, whereas with turbulence, the asymmetry is less. It's a very interesting result which we observed, and this measured, everything measured using, our this one. So to conclude, we have used a coherent wave field. We studied in passage through a turbulence using a simple PRPP in variance matrix. We can also use the uncertainty principle used to discriminate the data. We used actually the quantities of physical parameters. Interstice, twist parameters, symplectic eigenvalues, and wave field asymmetry parameter are studied. It is found that there is an enhancement of the fluctuation in all these parameters after the insertion of PRPP. On the other hand, it is seen that wave field symmetry on an average decreases passes through the PRPP. Our study can be extended to the scale of double passage, and one can also explore more general situations such as wave field through atmospheric turbulence and other kind of media. Now we have actually, what we have done is we are now using this different kind of beams. For example, Lager Gaussian beam, topologically charged beams, which are known as Lager Gaussian beams, where we found out that this parameter and symplectic eigenvalues and mean fluctuation of light beam are this actually, the turbulence is not affecting variance. That is, the turbulence will not affect the topologically charged beams compared to Gaussian beam. So here we have used simple helium neon Gaussian beam. So when this beam are changed to when this beam is this beam is changed to different topologically charged Lager Gaussian beam with different charges, we found that the impact of atmospheric turbulence is not much. Particularly, there are several papers in this area using Lager Gaussian beam, different topologically charged beams combined with a simple Gaussian beam. That the beam spreading, particularly scintillation, fluctuation, light, all these things are much less compared to Gaussian beam. So the new type of class bands like shell model beams, LG beams, which I have not shown here, these beams are very important parameters, which these beams actually will not be affected by atmospheric turbulence. Whether it is possible for you to use this different class of beams for adaptive optics, that's what our next we are trying analyzing and analyzing using in the laboratory system, and then we'll actually one way of doing it. Actually, you can convert. Actually, you can convert this light beam to LG1, LG2, LG3. Lager Gaussian beam, different charge beams using our spatial light modulators, and then you can also use some phase plate to convert this Gaussian beam into different charge beams, and then we can pass through PRPP, or we can use the light coming from PRPP, the turbulent impacted beam, which can be also converted to different topologically charged beams, and then whether it will affect the imaging quality, that we can study. So this is the idea here. Actually, this is a preliminary studies which we have, and we are also carrying out a lot of experiments based on twist parameter and symplectic eigenvalues and mean fluctuation of light, etc. So these values can be definitely used. These are fundamental parameters of light. Another important factor is that this is not a regular aberration of turbulence. The regular aberration of turbulence is piston, tilt of the beam, astigmatism, low order aberration, higher order aberration, all these things. So this is actually parallel measurements. So actually nobody measures this twist parameter, symplectic eigenvalues, and fluctuation, symmetry and asymmetry values are actually the in addition to conventional aberration systems. This also present in the light beam if you use variance matrix. So this is prominent only if you use variance matrix. If you simply use intensity measurements, you cannot calculate these three parameters, particularly twist parameter, symplectic eigenvalues, or mean fluctuation. You cannot calculate without substituting in variance matrix. So these are very important measurements based on variance matrix. In fact, that variance matrix are wonderful calculations given by Professor Mugutta and Simon. So this really helps us to deeply understand the light behavior passing through turbulence, and whether it is possible to use non-adaptive optics technique to correct these beams. That is our main important, and whether this can give you additional problems, or this will clearly clean the turbulent impacted beam, etc. So these things I will. What are the main applications of this one? So developing quantum equivalent for higher order aberration along lines of Zernike polynomial. There is one. Normally, Zernike polynomials are used for measuring this atmospheric turbulence, like piston and etc. These are orthonormal polynomials, Zernike polynomials, which I have not shown you. These are all orthonormal polynomials where one can use directly light measurements. You can fix in Zernike polynomial. There is a program you can measure it. But you can also try to equate, not quantum equivalent, but actually it is a classical measurements you can see. You can have this secret key distribution between two satellites with turbulence. This is one of the aims we can use using twist parameters. We don't need to go to quantum scale, and selection of appropriate adaptive optics for correction we can make. and selection of appropriate beams for imaging through turbulence also with much less aberration one can generalize, for example, Laguerre Gaussian beam, etc. With this thing, I thank you for listening.